Welcome to the video for implicit differentiation. We're going to be talking about this differentiation strategy. Let me tell you a little bit about why we need it. And here's kind of my motivating example. So how would you find the derivative to an equation where y is not by itself? Like this one, x squared plus y squared equals 25. Well, I suppose you could try to solve for y and then take the derivative, but why do more steps if we don't have to? What about if we had an equation maybe that's not as easy to get y by itself? What if we had something like xy plus 3y equals x squared? Could I really solve that for y? I mean, maybe you could with some factoring. What if I made that y cubed? Could you solve for y? Not really. I mean, you could still try to factor out a y, but you'd have y squareds on the other side. There's really no way to turn this into what we call an explicit equation. That's really the equations you've been working with all throughout your high school career. What an explicit equation is essentially a y equals equation. All throughout the course here in calculus, these are the types of equations we've been looking at. Y equals x squared, y equals the sine of x, y equals e to the 3x. They've all been in the y equals or f of x form. Okay? When you have an equation that is defined what we call implicitly, which basically means not in terms of y, we need to use what's known as implicit differentiation in order to take its derivative. Okay, so the whole point of that symbol that we've looked at before this year, that dy over dx symbol, the way we read that, remember, is we say it's the derivative of y with respect to x. It's basically saying that x is the variable I'm differentiating. I can still do that in an equation that is not in y equals form. How I do it is basically anytime I see the x, I just, business as usual, use all my rules that I've used before, power rule, chain rule, etc. But when I see a y in an implicit equation, I need to use the chain rule, and you'll see what I mean in a second, to show that I'm not differentiating with respect to y. I'm differentiating with respect to x. So we'll start with some basic examples. Here's what I mean. So here's the first one. The derivative with respect to x of x cubed. Well, the letter matches. So I can just use my power rule and it's business as normal. Bring down the 3, reduce the power of x by 1. The derivative is 3x squared. But look at the next one. D with respect to x, the derivative with respect to x of y cubed. For this function, I can't differentiate. I can't differentiate with respect to x because I don't have an x. So here's the best thing I can do. I can kind of treat it like a chain rule. What I mean by that is I can bring the 3 down like my outside function of a chain rule, 3y squared, but then I have to take the derivative of the inside function. And the best way to do that is with that dy dx symbol. Okay? This symbol is just basically saying I'm taking the derivative of the letter y with respect to x, and that's the best I can do because the letters don't match. Okay? We can do this by putting two letters together. I can use differentiation with respect to x. So the first thing I would do is do the derivative with respect to x of x, and that's just 1. Then I would do the derivative with respect to x of 3y, so plus 3, because the derivative of the outer function here would be just 3. But then I'd have to replace the y with the dy dx symbol to say, hey, they're different letters, so this is the best I can do to differentiate with respect to x. So to put that together, when we get to more complicated equations, how we would use implicit differentiation is kind of this 4-step approach, and I'm going to work through a bunch of these in this video using this 4-step approach. So step 1, I'm going to differentiate both sides of an equation with respect to x, and kind of like I did in the last slide, if we see an x, business as usual. If we see a y, we use our chain rule, and we stick a dy dx in as the inner derivative. So I'll do that to both sides of an equation. Then, any term that has that dy dx symbol right here, I'm going to collect all those terms to one side of my equation. The reason why I want to do that is I want to eventually try to isolate for this dy dx. Because remember, when we differentiate, what's the answer to most derivative problems we've done to this point, we have y equals, then the next line would say dy dx equals. My goal is to still try to do that. You'll see what I mean in a few moments when I try an example. So when I get all those dy dx terms to one side, I can factor them out, divide through by the rest of the stuff on that side, and solve. So here's what we mean. We'll start with a very basic example. We'll go back to the one that I started the lesson with and started the video with, the motivating example. If I want to take the derivative of this equation, first move I'm going to make is I'm going to just let my reader know I'm taking a derivative with respect to x of both sides. So I'm going to put this d dx symbol on both sides to say that's what I'm doing. All right, so this is the left-hand side is a sum. So I'll take the derivative of x squared first. Well, since the letters match, that's easy. It's just a power rule, 2x. Now, plus, because it's a sum, when I do the derivative of y squared, I'm going to treat this like a chain rule. I'm going to bring down the 2, keep the y where it is, reduce it to the power of 1, but then I have to multiply that by the derivative of the inner function, which in this case is dy dx. Now on the right-hand side, the derivative of 25, this is just a constant, and as we've said before, any constant has derivative 0. All right? So now my final step is algebra. I want to algebraically manipulate to get this dy dx that I've just underlined by itself. So first move is I'll subtract 2x from both sides. I get 2y times dy dx equals negative 2x. I'll divide through by 2y. I'll cancel out the 2's, and I get that dy dx equals negative x over y. We'll talk more about what this means in terms of slopes of tangent lines, equations of tangent lines later. The whole point of this video is to just get you through the mechanics of implicit differentiation. So I know that looks funny and it looks like there's more you need to do, but trust me on this. I got dy dx by itself. I'm done. Let's try another one. Okay, this one is not as cut and dry because I have letters on both sides. So we'll start it the same way as before. I'll differentiate with respect to x on the entire equation. The first piece, the 3y squared, is a chain rule. I'll take the 2, bring it down with the 3, multiply them together to get 6y to the first. But then I need that dy dx piece to do my inner derivative for y. Next, I'll take the derivative of 2. Well, that's a constant. That's 0. I'm just not going to write it. I'm going to drop the 2 out in this line. Now, when I do the derivative of 8x cubed, since the variable there is x, and we're differentiating with respect to x, this is just my normal old hat power rule, 24x squared. Okay, so there's really only one step here to get dy dx by itself. It's divide through by 6y. Do a little reducing. Dy dx is going to be 4x squared over y, because the 24 and the 6 can reduce to 4 over 1. Okay? Let's look at one more. Okay, here's one that's not quite as cut and dry because I have x times y equals 8. So again, could I divide through by x and differentiate that way? Sure, but let's practice the implicit just so we understand how it works. Okay, so I'm going to take the derivative of both sides with respect to x. Okay, so I have two letters being multiplied together, and I want to take a derivative of that product. I wonder what I got to do here. I think I got to use the product rule. So we'll do the derivative of the first term, which is just going to be 1, times the second term, which is y, plus the first term, which is x, times the derivative of the second term, which is going to be written as dy dx, equals the derivative of 8, that's 0. Okay, so now my goal is just do some algebra to get the dy dx by itself. I'll subtract y from both sides. I get x dy dx equals negative y. I'll divide through by x, cancel out. Dy dx equals negative y over x, and I'm done there. Okay, let's try one more from the video, and then I'm going to think that's going to be enough for you to at least do a little bit of practice with this on your own. Okay, this is as hard as it's going to come. Okay, it's not going to get much harder than this. I'm going to try to work through it slowly. If you need to rewatch this example, please do. This is kind of like the highest level for right now of implicit differentiation. But I want to show you one here. And this is kind of where we're going to pick up with practicing this in class, okay? So I've got x squared y plus y squared x equals -2. Here's the reason why this one's a little bit more challenging. When I take the derivative of both sides of this equation, notice what I have going on the left side. I have x squared times y squared times x. I have a double product rule. So we'll take it one at a time. We'll start with the x squared y product rule. So I do the derivative of the first term, which is x squared, which differentiates to 2x, times the second term, y, plus the first term, which is x squared, times the derivative of the second, which will be dy dx, because that's the best I can do because the letters don't match. Then I've got to do plus the derivative, let me use a different color so you can see what's going on, plus the derivative of y squared x, which again is a second product rule. So I'll do the derivative of the first piece, y squared. That's going to be 2y dy dx times the second function, x here, plus the first function, y squared, times the derivative of x, which is 1. And all that is going to equal the derivative of -2, which is 0. Okay, so let me do some cleanup. Let me go back to one color. I'll switch to black. So I've got 2xy plus x squared dy dx plus 2xy, because I like to collect the letters in front of the dy, plus y squared equals 0. Okay, anything that is not a dy dx term, I'm going to ship it off to the right. So I'm going to subtract y squared. I'm going to subtract 2xy. I'm going to do that from both sides. And I get x squared dy dx plus 2xy dy dx equals -2xy minus y squared. Now that I have dy dx is all on one side, I can factor them out and treat it like a GCF. So I'm left with x squared plus 2xy equals -2xy minus y squared. And then I can divide through by the x squared plus 2xy on both sides. And now I'll finish it up top here. My dy dx, the derivative of that function, can be represented as 2xy minus y squared all over x squared plus 2xy. And if you're a savvy algebra student, you can see that I can do a little factoring. Up top, I can take out a -y and write that as 2x plus y. And on the bottom, I can take out an x and write that as x plus 2y. All right, when we start doing some application problems, it might make sense to do that factoring. I know usually we only factor so that we can cancel, and you notice nothing really cancels here, but it might make sense for you when we do some application problems, some plugins, where you need to have it in factored form, so that's why I want to show you that step. Okay, for right now, this is about as challenging as it's going to be. If you have any questions about this, we're going to do lots more examples of it in class. Your notes sheet has a few more examples that I want you to try on your own, and we'll go over those in class. Okay? With that, I wish you a great evening. Thank you for watching the video, and I will see you in class.